In this video I will talk about central limit theorem. This is one of the most fundamental results in statistics. Almost every statistical package that you know of uses central limit theorem. Okay, it says the following. Suppose Suppose you have a random sample from a population with the population mean equal to mu and the population variance equal to sigma squared. Then the central limit theorem says the following, that x bar is the sample mean minus mu divided by this, right, approaches the standard normal variable as n approaches infinity. Right, so this is, some of you know this, probably know this already. So x bar is the sample mean. Right? And mu is the population mean, as we just mentioned. Right? And this guy here, sigma by root of n, is known as the standard error. And this is one of the most celebrated results in statistics. There's not a book in statistics that doesn't state the central limit theorem. Right, the next thing I'm going to talk about is how to use the central limit theorem to come up with the model for sums of independent random variables. Okay. So this is a model based on the central limit theorem. Okay, let n denote the sample size. Okay. N is can never be infinity. I mean, all the data sets that we have in real life are finite data sets. They can never be equal to infinity. So in order to use the central limit theorem, we need to assume that n is a big number, so that the left hand and the right hand sides are equal. Right? So suppose n is large enough. The word large enough is debatable, but it could be like anything. In statistics, we say anything above 25. Anything about 25 is large enough. Okay. Right, suppose n is large enough that the central limit theorem holds. Right? In other words, the left hand side, which is this one, right, can be approximated by the right hand side, which is the standard normals. So this notation here, whenever I use this notation, I mean approximation. Okay. All right. So suppose these two are equal approximately. Right? So this implies that the probability is approximately equal to the CDF of this, which is, I'm sure you know, is phi at x. Okay, so this implies that the probability that x bar is less than or equal to mu plus sigma by root of n times x is approximately equal to phi at x. Alright? Okay, now before I go to the next step, let me call this guy here equal to y. Okay? So if this is equal to y, this will become the probability that x bar is less than or equal to y, yeah, approximately equal to phi. Now x in terms of y is going to be the following. Right, you see, if you express the x in terms of y, this is what you will get. Okay. Right. Now, let me write x bar as the probability 1 over n times the sum of xi less than or equal to y, right? Approximately equal to phi Now I'm going to bring n to this side, so this becomes okay. All right. Now I'm going to make another transformation or substitution. Let me call this here equal to z. Right. Right. So y will be z divided by n. Right. So this will be So this, when I say a model for based on CLT. This is what I meant. So what I have here is the probability of a sum of independent variables less than or equal to something, a fixed number, approximated by this, right? And we can use this result to answer example 3 from the previous video, right? And that's what I'm going to do right now. Okay, so I'm going to use this result to answer example 3. Okay. So this is example 3. Right, so I'm going to. This is a continuation of example 3 from the video on binomial distribution. Right. Okay. So suppose suppose you have x1 to xn which are independent and identical Bernoulli variables, right? Okay, so that means I don't know whether you know that a property of sum of Bernoulli random variables is the following: that if you sum IID or independent and identical Bernoulli random variables, then what you get is the binomial distribution with parameters 1000 and p equal to 0.2. This is a basic property. You should have learned this in probability 1. Okay. So what this means is the following: that using the result that I proved in the previous slide, okay, we can say that the probability of a binomial variable with parameters 1000 and 0.2 less than or equal to z, okay, is approximately phi. Okay, your n is in this case 1000 divided by sigma times z divided by n minus mu, right? Okay. Now, the question that we wanted, the question that we wanted to answer is the following: we wanted to find the probability that a binomial variable with parameters 1000 and 0.2 lies between 100 and 200. Okay, so this you can write as the difference of these two probabilities. Right, this probability minus the probability that a binomial variable is 99 and not 100, because in order to include all the numbers from 100 and 200, you need to take away this probability that is less than or equal to 99. I hope you follow me. Yeah. All right. Now, using let me call this equation here star. Okay. Right. Using star, so I'm going to use star here. Okay, you can approximate this, so I should use approximation. Approximate this right, and minus okay, now before we can proceed, we need to compute mu and sigma. Remember, mu in the central limit theorem, mu is the population mean and sigma is the population standard deviation. Right? Okay, now in this case we are talking about a population that is Bernoulli with parameter equal to 0.2. Right? So basically the population mean is the mean of a Bernoulli variable with parameter 0.2, and sigma is the standard deviation of a Bernoulli variable with parameter 0.2. Right? So that's what I'm going to do now. Let me take another sheet here and put it here. Mu is the expected value of xi, where xi is a Bernoulli variable, right? And because and you should know the formula for the expectation of Bernoulli is p. In this case, p is 0.2, and sigma squared is the variance of xi. Now, once again, you should know the formula for the variance of Bernoulli variable is p times 1 minus p, so which in this case is 0.2 multiplied by 0.8. So sigma is simply the square root of 0.2 times 0.8. Right, so let me put this in a bracket, in a box. Right. Okay. All right. Now I can substitute these into the equation, into this equation, and you will get the following. You will get phi square root of 1000 mm. 200 divided by 1000 is 0.2, mu is 0.2, okay, minus 99 divided by 1000 is 0.099 minus 0.2, right? Okay. So the first term is 0, right? Because 0.2 minus 0. So phi of 0, I'm sure all of you know, is half, right? So this becomes 0.5 minus this guy here, which is, we'll just write it down as it is. Alright, so you can read this if you have a calculator, or if you have the tables with you, which I showed you. If you look at the video for the normal distribution, I showed you the normal table. So you'll be able to read this from that table, and then you can compute what this is. Right? So calculate using normal table. So once again, you should look at the video on the normal distribution. You will see the normal table, right? And you should be able to read this from the normal table. All right. So this completes the video on the central limit theorem. And in the next video, I will talk about sampling distributions.